anyways, reward is not necessarily an opinion that sort of falls out of this perspective that I'm going to present. Okay. Let's see. All right. So yeah, because this conference is, or this workshop is about the what, how, and when of learning, I'm mostly going to talk about the what and the how. So the what, I'm going to argue that that it's very useful to produce state-time feasibility functions, and I'll tell you more of what this is. And the how, I'm just going to tell you about the model-based dynamic programming principles. So it might be true that you could, compute these in other ways from experience, but I'll just tell you about the model-based foundations. And the reason is because that we're going to talk about this is because it makes it really easy to plan with sort of dynamic product spaces, which I think is sort of characteristic of the world and also your internal state spaces. Okay, so let's think about a simple task. So we have a hiker here, and this hiker has some low-level state space, is in some low-level state space X, and has low-level transition dynamics here. The hiker also has a hydration state space and a hydration state space transition operator, TW. And the G here, I'll talk about that in a second, but so the hiker also has a caloric state space, Y, and a transition operator for that, and a temperature state space, Z, and a transition operator for that. And all of these are indexed by goals. And so goals are going to be actions which act on this space. Okay, so goals are going to come in two types. There's G+, which is like an active action. So if you drink water or eat, or you use the warm action, it's going to jump you up in this space. Or there's a null action, G epsilon, which is going to produce the natural dynamics of the space. So if you're moving around, you'll just get progressively more hungry over time, or more thirsty over time. And so there's going to be a function, a goal availability function, which is going to emit these actions from low-level state actions in this space. So whenever you're not at like some feature like this, like drinking water, you're going to emit a null action. And okay, so if you drink in this framework, it's just going to take you to the top. It doesn't have to take you to the top. It could take you like up 3, but here we'll just say you become fully hydrated. And if you emit a null action, it's just going to descend you down this state space like this. And so it's critical to notice that we're really working in a huge product space. So this already, just for the simple example, is about 55,000 states. And if you think about like all the state spaces and all the states that you could ever be aware of in your life, it's much worse than this. And it can be a function of time. So how do you deal with complexity like this? Okay, so let's say that the hiker who's is close to being dehydrated here at the bottom is going to go up to this lake to drink water. So the hiker moves up to 2 states. And let's assume that we have this function, the state-time feasibility function, which I was telling you about. So this function, which I'll tell you about how to compute later, is a map from your initial state time to your final state time. And it takes in a policy as an argument. So it's just going to map you from this state time to this final state time in one jump, and the corresponding action that's going to be produced that's going to act on this higher level state space. Okay. So if the hiker moves 2 steps up, it's going to go 2 steps down, and then it's going to jump up. So it's going to go like this. Does that make sense? So what's happening to the other state spaces when this happens? Well, if you're moving 2 states up, you're emitting these null actions, and they're all going to affect the other, they're all going to enter into the other dynamics of this space, of these other spaces. So they're just going to descend. 2 steps for making it to the lake, and then 1 extra step, a 3rd step, for when the agent drinks water. So if you think about, just have, all right. If you think about this, you just have null actions when you're moving from here to here. This is really just a Markov chain, right? It's the null Markov chain of all of your internal states. So if you have G epsilon for each one, we'll just call this the null Markov chain. And this means that we can take the time difference from the state time feasibility function, right? So we know the initial time and the final time, and we can just take this Markov chain to that power, and that will just give us a map to where we'll be once we finish this individual goal. Yeah. So omega is another sort of jump operator. So it's just going to map you from your initial state. And I should really just have a big arc here that goes down 2 steps, but it's going to map you 2 steps into the future. And then there's 1 additional step. So what that looks like is that all of these functions we've been talking about are sort of form a composite jump operator, but we can represent it in this factorized form. So if we have this state time feasibility function, we just compose it, and we're just focusing on x, y right now. We're not talking about the entire state space right here, but if we compose it with omega y, and then we update it 1 step. So this is the 1-step update after you drink water. Then we form this operator. But no, we don't have to store this entire operator, right? We can just store everything in this factorized form, and just forward evolve all of these operators separately, right? So you can do this for all the state spaces that you care about. And so we'll call that R. So R is just the state vector of all your internal states. And so TR is just going to be the product of all your internal state spaces, transition dynamics. And omega R is just going to be if you compute this for every single internal state space, right? So you can substitute, you can imagine that when you form this for R, you substitute these things into this expression, it can get very big, but you just have to represent these things and propagate them locally. Okay, so now the agent is going to want to eat, so it goes over to the apple tree. And so you can just get an updated dynamics just from sampling from the operators here. Yeah. So this is under pi G3. Then the agent's going to want to return home, and gets home, and now the hiker is warm. So this would be the sort of final state vector of just following pi G2, pi G3, pi G1. So it's like a sort of open loop plan. Okay, let's consider a different hiker who's very hungry and is about to hit the starvation state in four steps. So wants to get food as soon as possible. So it's going to go to the closest tree, right? And then he's starting to get thirsty. So he goes to the water, right? And then you'll notice that the hiker is now very, very far from the house, right? So what's going to happen? Well, the agent's going to pass through like the bottom state. And one thing I haven't talked about, and I won't talk about the formalism, is, but it's possible to take these states, like the bad states, and basically make them arrest your dynamics. So like if you hit these states, you're immobilized, right? You're dead and you can't move around the state space, right? So it's possible, for instance, for, if the agent were to try to use this policy, it would just die here. So you can use this framework to sort of reason about sort of avoiding these bad states, right? Okay, another thing you can do that's, let me move this a little bit. Okay. So another thing you can do is just simple logical planning. So if you have like a bit vector space, these bit vectors aren't dynamic. So if you just have to collect items, like collect an apple and a key in water, essentially you can use the same sort of update rule. You just don't need the forward prediction in these latent spaces, because these are like stable states. So they'll always persist. Okay, so for instance, you can go get an apple, and so it moves you, it flips the one, and then you go get water, and it flips this one, and you go get the key, and then you satisfy your objective, which is to get these 3 items. Okay, so you can plan through, for instance, like a hypercube without representing it this way, and these can also be functions of time. Maybe the key's only there for a certain window of time or whatever. Okay, so now I'm going to talk about how we compute this feasibility function. We've seen that it sort of helps us like plan in these large product spaces and do all these updates. And this is a very important point that I want to make. It's that the model-based principles that you use really matter in creating like interpretable like representations that you can reuse, right? So we're all very used to this is the standard infinite horizon discounted Bellman equations, right? Where you have an optimal value function, which is just the reward you get, at some state action, plus the expectation of the future discounted. And you'll have like an optimal policy based on that. But value functions they're not really composable, with the assumption of Emo Todorov's linearly solvable Markov decision process framework, which Payam will talk about later. Value functions in general aren't really composable, right? They map you to just a number, and that's the domain isn't like an input to some other thing. So you can, I'm going to introduce what I call operator Bellman equations, which preserve the interpretation of an operator. Okay, so this is a non-stationary Bellman equation where we're going to have a cumulative feasibility function. And so we're going to maximize the cumulative probability that we're going to achieve some goal. Okay. So you'll notice here's our availability function, which we were talking about before, which is omitting goals, right, from the low-level state space. So either the goal is available with some probability at some time in the state space, or it's unavailable. So either you achieve it now, or you don't achieve it now, but you multiply the expectation that you'll achieve it in the future, right? So there's also a secondary objective on the policy, which isn't standard, but basically because like if a store is open from like 3 to 8, you can maximize the cumulative probability that you get an item from the store by getting it right before it closes, if you know that you can do it, or you can get it as soon as possible. So you can choose the actions which minimize the time while maximizing the cumulative feasibility. So this is sort of conditional. A star here is just the set of actions that maximize that equivalently maximize the cumulative. So you're just optimizing over this set. So this is kind of like a conditional optimization. And so this is just the expected goal satisfaction time. And so in this framework, we have a third object, which is the state time feasibility function, which you can just update as you compute these other 2 things. So this is the primary objective, but the state time feasibility function, as you update it, backwards in time, backwards induction, has this relationship to the cumulative, right? So the if you have some state time here and you have the same state time here, you're just summing over the final times. So the cumulative feasibility function is just the sum over the final state time probabilities. Okay, so what this means is that you can, how am I doing on time? Yes, a little bit. So you can compute a set of feasibility functions, right? For one for each goal here. And then you can make a composite feasibility function, right? So each of these have a single policy attached to them implicitly as a variable here. But now you just use these variables as inputs to a composite function, right? And so that's what's mapping us around in these in the previous slides. Okay, so here's the connection to things that people have been talking about in the past, like yesterday. So Daniel Polanyi talked a little bit yesterday about empowerment. I don't think he talked too much about its definitions and stuff like this. But empowerment, if you weren't here listening to Daniel, empowerment is basically a metric on a transition operator, right? So it basically tells you how much can this transition operator do reliably, in a sense. So under deterministic conditions, this reduces down to something very simple. And that is the empowerment, the n step empowerment, so that n is a horizon parameter, is under a deterministic operator T, is the number of states, reachable states. It's the log of the number of reachable states, is what I should say. So xn here is the set of reachable states, so the cardinality of it, and so log of that is actually equal to the empowerment. So this is just saying this operator can do this much, and because it's deterministic, it's all certain. And so what you can do is you can create what I call a valence function, which is just the empowerment difference from where you start now and the empowerment from where you are. So you have an n-step empowerment like right where you are right now, and then you can plan into the future like we've been like selecting these policies, right? I'm going to follow this policy, I'm going to go there and at this state time, and I'm going to go there and end up at this state time. What's my empowerment? What's my n-step empowerment there? So rho here is just, I didn't put it down, but rho is just a sequence of policies. So rho is like a plan. And so S rho is just the state that you end up at after following that plan, and T rho is the time. So what that means is that you can basically have an evaluation function on these plans. So you could, for instance, use breadth first search to sample the space of sequential plans, right? And here I'll just show you two. So you have two hikers, and one of them, and so both of them are like 2 steps away from the starvation state, which is going to immobilize them, right? So there's a bound on what it can do before it's like technically dead, right? And so you can see in pink this is the size of the reachable states here. And so that's log of 13, because there's 13 here. So that's the initial empowerment. So if you map forward in time, this hiker will end up here, and its temperature will be state will be one away from like freezing to death. So that means it can only go like 1 step. So it has the final empowerment of log 2 of 5. And so its valence is negative 1.37. Okay, but you can now do this with the other guy, and he'll move down here, and you'll say he's 3 steps away, right? But this, and you can see in the area here, the number of states he can reach is much bigger. So it's log of 25. So this means his valence is positive, right? It's 0.94 because he started off with a smaller valence. But you also notice that this covers a lot of sort of items in this space. And my time is up. I'm like almost a minute over. But you can basically select plans like this without a reward function. So there's no reward function in the Bellman equations, which produce these operators, right? That's reward free. But the operators were crucial for evaluating empowerment. So my claim is I actually think that you can do artificial intelligence this way. You can it gives a normative reason for creating these abstractions, right? Because it allows you to justify states that you might have never reached in like a large product space. Okay, so intelligent systems operate in high-dimensional product spaces with non-stationary dynamics. Operator Bellman equations have a different form from infinite horizon, which produces transition operators. Transition operators are composable and reusable and can be remapped to different transition structures. Forward sampling is a good way of solving problems in a high-dimensional product space in a factorized form. And because empowerment is a function of a transition operator, you can even compute it, on these jump operators. So I was computing this on these low-level operators, right? You can also just work in the space of tasks, right? So you can work at long time ranges, things like that. Okay, that's all for me. I will take questions later because I'm 2 minutes over. But thank you for your time. You can check out some earlier work here, jump operator planning. And the stuff I just talked about will be on archive soon, and I'll probably tweet it out. Thank you.